What's up, everybody? This is Matt Brown with part 2 of Enterprise IoT Pentesting, where we are performing a case study on this UniView camera. In this video, we will get a root shell on this device by exploiting an unlocked bootloader and a path to getting out of a jailed shell environment and having a full root shell on this device. This video is all about hardware enumeration, and we are going to dive into the process of hardware enumeration in an IoT pen test, and then we're going to go to our case study target over on the workbench. If you're new to this channel, my name is Matt Brown. I am an IoT security professional, a content creator, and a bug bounty hunter. I have found lots of 0 days in big name IoT devices out there, and so this is what I do, and I love to teach you about this process. So without further ado, let's jump into it and talk about the first step in the technical portion of an IoT assessment. So in the last video, we talked about some of the pre-assessment activities, determining what the scope of the assessment's going to be, the timeline, budgets, those kind of parameters, even talking about the threat model of our device, what vulnerabilities we care about, what we don't care about, what we really want to get out of the assessment. Once we have that in place and we've kicked off the assessment, the first thing that the pen tester is going to do is they're going to perform hardware enumeration here. And so when we do that, at a high level, I like to start here, which might seem like a strange place to start, kind of bifurcating the IoT pen testing into two different device types. But this is really helpful for me, and I think it's helpful for other people who are learning as pen testers to know where you need to get level up your skills. And so you kind of have your traditional microprocessors devices that are running Linux, Android, a full-fledged operating system. These are usually more resource intensive. They have network services, lots of processes running on the system, oftentimes more storage, and these are usually hardwired devices. Again, there's caveats here. Some of these properties fit into the other categories, but you get the idea. Whereas on the other side of the fence, you have microcontrollers that are going to be like a bare metal, like an ARM Cortex-M. You might run a real-time operating system on top of that bare metal system, and so these are usually going to be found in portable, battery-powered, small devices that want to sip on power. And so those devices have different threat profiles and different skill sets you need to attack them. So I just like to start by identifying what type of device you're looking at in any IoT pen test. And then you kind of have some of the practical stuff, which we're going to see over on the workbench. You got some screws. You gotta take stuff apart, right? This is kind of common sense, but if you've done this as long as I have, you accumulate tools that look like you're about to rob a very particular kind of bank. I've got a Dremel. I've got different prying tools to open up cases that are glued shut, for waterproofing purposes, things like that. Once we do that, once we get the device open and we get inside and we get to the circuit board, this is really what we want to get to. And oftentimes, I'll make a point that I don't have here in my slides. You want to get the device into a functional state with it outside of the shell. Now, depending on the device, that can have a whole bunch of complications. Potentially, you want to power the device with a bench power supply like I have over here instead of the traditional power supply for a whole bunch of reasons that might be complicated. But you usually want the device to be exposed when it's running so you can do a lot of this testing that we're talking about here in this slide. So the first thing that I do when I open up a device, I want to identify all of the important chips, the important components on that circuit board. So we're looking for, again, the CPU or the MCU, and that's where you start to find out when you open this device is it a microcontroller? Type of a system, or is it going to run Linux or Android, something heavier? And then you're also looking for flash chips, right? Where data is stored in a discrete chip that can be read with a number of programmers. We are going to talk about firmware extraction completely and do a deep dive of that in the next video. So I'm not going to talk too much about that right now. But then we're also looking for different debug headers. And so we have UART, which is a common interface that we are looking for that allows us to interface with a device's serial console, potentially. And we're going to see that. Obviously, we've already foreshadowed that a little bit in our UniView camera here. We're also going to want to look for debug protocols like JTAG or SWD. This is going to be much more important, not that it doesn't have security applications in the, like if you're attacking a Linux device, but if we have a microcontroller target, oftentimes there is flash storage internally within the microcontroller. Whereas on a Linux system, it's a discrete chip that you can easily desolder and throw in a flash reader. But oftentimes the only way to get at the memory, the firmware of a microcontroller is through one of these debug protocols. So we want to check if those are enabled. Obviously, we're going to write that up as a finding if those interfaces are enabled, if those protocols are enabled. And then if we can get firmware off, then we're going to look for other vulnerabilities in the system from there. And then obviously at this point, we're going to do all sorts of open source intelligence. We're going to look for data sheets. Sometimes you can find those publicly. Sometimes you can find them in, more like gray areas out there on the internet. And sometimes they are completely locked away behind, a paywall or a NDA or both. So that's enough slides. Let's get over to the desk and let's open this device up and show you how we do this. So I've got a couple of things here. So I have my UART adapter. This does a lot of other things other than just being a UART adapter. But this is a TiGuard, and so we're going to use this in a little bit. This has been my new go-to UART interfacing tool. So here is our camera, and then I also have, just my iFixit screwdriver set here. This is nice because it just gives me all the bits that I would ever encounter on one of these devices. Obviously, you can get a cheaper solution out there and probably throw something together, but I do just like it. So this one, it's got this weird little screw here, and then this. Let's see if I can do this live here. Get it to the point where it unlocks. There we go. Set this off the side. All right, and we're going to see here that we can get this outside of the housing. So the whole point of this housing, right? This is not a pan tilt zoom camera. It doesn't have motors that move the camera around. And kind of a fun fact about most cameras in the security market, they don't actually do that. If you like go someplace and you see a bunch of dome cameras sitting up, they are oftentimes to obscure the fact that they are fixed cameras and to make you think that they can see from all sides, but in fact they can't. So here we've got 3 screws here in the back, or at least there was 3 screws, and honestly I lost one of them, so we're gonna take out 2 of these screws here, and then I think I might have to take off this little back cover, which is where you get access to, I believe it's like the factory reset button and the SD card. Actually, oh no, it comes off just fine. Okay, don't need to take it off. Here we go. So now we are inside of our camera. And so in our last video, we noted that this camera is power over Ethernet. There is also a power adapter that I was not supplied with when I purchased this camera. I'm pretty sure I could look up what that is. But over here on my desk, let's zoom out. I just have this cheap little TP-Link PoE injector. So on one side, I have my network monitoring infrastructure, and then on the other side is the Ethernet cord. So when I want to go ahead and power this, so I actually don't have that turned on right now, so I can go ahead and plug this in, but it's not going to power it on at the moment. So now we have our device. Let's zoom in and see what we are dealing with here. So right out of the gate, I see some things that are super interesting to me if I am taking a look at this device for the first time and enumerating its interfaces. So the first thing I see, there's a couple. Okay, so first I see a discrete flash chip here. So you can see this is an four pads on this side, 4 pads on this side. So this is a standard 8-pin. This does happen to be a NAND flash chip, and so if I wanted to get at the firmware of this device and I did not have any other way to get access to it, a little foreshadowing there. I would be able to desolder this chip off the board and gain access to the device's firmware. Also, very useful, we will actually use this later, is this SD card slot. So I do have an SD card in there that I've been messing around with. And then the other really important thing for now is over here. We see unpopulated these 4 through-hole locations for pins, and so we're actually going to take a closer look at that with our microscope. Let's pull that over here, and that's going to be way too close. All right, yeah, we're probably not going to get this in focus, are we? We're gonna try our best. Hey. Okay, that's gonna be very blurry. Ooh, there you go. So I probably need to take this circuit board off of here to get a better shot. But we can see semi-clearly that there are 4 pads here. You know what? Yep, we are gonna take this off so that we can get better access. All right. Because we are going to be interacting with that interface because, as we kind of talked about in our slides, one of the interfaces we always look for especially on a Linux-based device, which, spoiler alert, that's what this is UART. And UART usually shows up as a set of 4 pins, which is why like my eyes just kind of directly go to that spot on the board. One more screw. That is, so that's where we're going to start probing around with our multimeter when the device is running, try to determine the pinout of that interface, and then use our handy little UART adapter over here to actually interface with it. Okay, so I took 3 screws out. Yeah, all right, so we are going to do this. We're just gonna... Actually, we're just going to do it with, we're not going to do it under the microscope because that is going to be a pain to get that set up to where it will focus. Is this the right screw? All right, we're just going to throw 1 screw back on so that kind of stays in place. And then we'll use this guy right there. All right, but you can kind of see those. And then we're going to enable our little overlay here. And so currently don't have the device powered on. And the first thing I want to do with our 4 candidate pins here is I want to figure out which one is ground. Now, when I'm actually interfacing with that UART interface, I'm not going to connect to the ground interface there. For practical reasons, I could, but there's just so many other areas. So shielded components are oftentimes grounded. So the top of this SD card adapter, and then I've got this metal housing down here. And we can see from the beep and our on-screen overlay that those are both grounded. So now what I can do is I can hold on the SD card slot and I can probe here. Nope. And all right, so that top pin is ground. So that means I don't have to worry about that. So I've already eliminated 1 out of 4. So what we're trying to hunt for at first is the device's transmit pin, because what we're going to look for is a fluctuation in voltage, especially when we boot up the device. So now we're going to change over to voltage mode, and I am going to power on the device. So I'm gonna be off screen here with my hand, powering on the device, and then I'm gonna quick come over and see if we can find where the UART is. Okay. So we're good. We powered on. We're at 3.3 volts. Okay, that one seems it's just holding steady there. And that one you see jumping around. So that is a telltale sign that we have found the transmit pin. And then another thing we've done at the same time, simultaneously, is we've confirmed that the voltage of this UART line is 3.3 volts. So I'm actually going to go ahead and power this device off, and we're going to get our UART interface set up. So right here, I need to plug these in. All right, so I have, I'm connected up on my little board here. Let's get a good shot of that. To TX, RX, and ground. So green is ground, and yellow is our RX line. So I want to plug yellow. I want to connect that up to what I think is the transmit pin, which is the second from the bottom pin over here on our board. So we also need to connect up to ground. And so, like I said, we're going to work smarter, not harder. So I have that connected here, and I'm just going to plug it to this little alligator clip here. And since I know that this base plate down here is grounded, I'm just going to connect to that, because these other ones are going to be a little trickier, and that's where we're going to use our PC byte probes. And so this has a spring-loaded needle on the end that is going to allow us to, without soldering, connect down here to our interface. So let's go ahead and do that now. Again, right now we're not going to worry about transmitting to the device. We just want to receive. And I'm just going to rest the pin there. And I just realized that what I should have done before that is plug in, because I might bump it now, is plug in the USB cord to my tie guard here. All right. So just to zoom back, all I did is plugged in USB. And the thing I really like about this tie guard, instead of the dedicated, single voltage UART adapters, is it has a toggle switch right here. So I can make this be 5 volts, 3.3, 1.8, or take a reference voltage. So this in one device, it'll do all those different UARTs, which is nice to have. All right, so I think I'm still connected up to there. And let's come back over here to our computer. And first, okay, so my adapter is plugged in, and we can see here in dmessage that it has showed up here. It is connected. And it actually brings up 2 serial interfaces. And so the first one is the one that is like the standard UART. I'm guessing the other one is for programming the device or doing other things. The tie guard board does way more than what I'm using it for here, just to be clear. But yeah, it's going to be TTY USB 0. So the way that we interact with this, the way I use is we need a terminal emulator. I use PicoCom, and then we need to set the baud rate. 115/200 is like the most common baud rate out there, and if you're on a target and it's not that baud rate, or you think you don't have the right baud rate, you can look at tables of other common baud rates, or if you really think it's something weird, you can hook up a logic analyzer and actually look at the UART signal. But we're not going to get into that here because everything is pretty default. That's something else I had pasted. All right, TTY USB 0. All right, so it's ready to go. And now what I'm going to do over here is I'm just going to power on the device. I'm going to turn on my power strip here that the PoE injector is plugged into. And if everything works correctly, we should see output. So that is awesome. And so we see the device booting up, and I'm actually going to So it's going to scroll, 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 but I'm going to scroll up, and we're going to identify something that we are going to target. So right now, I don't have the other pin connected. So I don't have my TiGuard's board transmit pin connected to the receive pin on the board. So we need to find which one that is. And sometimes it's just a 50-50 shot to figure out which one is the VCC pin and which one is the receive pin on the board. Sometimes the receive is like floating around, but sometimes it'll just show up as 3.3 volts on a target board. But we're going to look at this output and see something that gets printed that catches our eye. Or at least it did. Now it's not. Now I'm not seeing it anymore. All right, where's our prompt? So we do see that it is running U-boot, which is a common open source bootloader for Linux-based devices. And where is it? All right, come on, man. Somewhere here it said press. It said the key combo to press to pause the boot process. All right. But we'll figure that out. I'm pretty sure it's Control B. I saw it and now I'm not seeing it. I'm blind. All right, but let's go back to our bench and let's get this other one connected up. So kind of show you the wide shot and then we'll show it up close. So we've got this other pogo pin adapter, and I'm gonna spare us the annoyance of me like trying to connect up to the wrong one. I just know that it's this other one right here. All right, there we go. And I think we have a decent connection there. So we will find out by hitting enter. And we have input now. So now we have, TX and RX available. And so what I can do now is I can turn the device off and turn it back on again. And I can hit Control B. There we go. Okay, here's where it said it. So press Control B to abort auto boot. And so different bootloaders on these systems have different key combinations, so oftentimes you just want to like try a bunch of them. Oftentimes you can just hit anything, and if it detects any kind of key press at all, it'll stop. But in this case, it was Control B. So once we did that, it stops the boot process, right? It does not boot into the Linux kernel yet. And then we can run the help command, and this handy little help command, it can tell us how we can interact with this system. And so we are going to, the first thing we're going to do is we're going to run the print env command here. So here we see a bunch of environmental variables that are set in the U-boot for the U-boot environment. And so things like baud rate, and then right here we have what's kind of the most critical here. So here we have boot args, a bunch of stuff, and so these are all of the arguments that are passed to the Linux kernel. And so this is where we can modify things in order to get the device to not boot normally. Because if you noticed, when we let it boot up fully, it had a username and password. We had to log in, right? And so on this system, we want to pause the boot process, and actually what we're going to do is we're actually going to allow it to boot, because we're going to show the full range of the problem here actually. So we are going to run this custom command to fully boot the device, and we're going to observe something that occurs because it's very important to point out. All right, I'm going to get something loaded up. because we're going to be pasting some commands in here. All right. There we go. Okay, we got our login, and I actually have configured this camera already. So I know the web GUI's password, admin password. And so I'm going to type admin and then password. Okay, I think it is the root user and not. Okay, there we go. Root. Here we go. Okay, so I am able to log in. But there's a catch. So if we try to run like some normal, you're like, wait a minute, that's not the correct output of that command. You know, can I see what's mounted? Wait a minute, what's going on here? No, not support command yet. That's a great output. All right, trusty help command here. Wait a minute. So we are in a jailed shell environment where they are kind of hand selecting, they're whitelisting what commands we are allowed to run, right? So when they do this, inherently they're not giving you a full root shell, and they're especially not giving you commands that would allow you like raw access to, say, the device flash, to be able to dump the flash off the device, to perform further security analysis. So this is not the most useful shell to us. So if we could escape out of this shell, that would be very helpful. Now, to be clear, that username and password, I set the device. That in and of itself, this access to this shell is not a vulnerability, and but we do want to be able to escape out of this shell. So that's where we're going to reboot the device, hit Control B, and we're going to use our bootloader access. Did I get it? There we go. Okay, we're going to use our bootloader access in order to get us out of this jail that we're in. So, first thing that we got here, just need to consult my notes. So yeah, print env, and then I'm going to just make a little text file here where we're going to grab these boot args, okay? Because we want to modify the boot args, and what we're going to do is we are going to add an argument here. So sometimes what you can do is you can modify the init variable. Let's just go there, right, like that. Sometimes you can modify this variable right here, and that will, you can set it to like bin sh or something like that. I found on this device I actually wasn't able to do that, but there is a directive called single, which will boot it into single user mode, which will effectively like drop it into a shell instead of executing kind of the traditional Linux init system. And so this is what we want our arguments to look like. And so we are going to actually just get this command ready. So there is another command up here. Oh, we run help, called set env, to set an environmental variable. So what we're going to do is we're going to prep that command down here in our text editor. So we're going to do set boot args, and then it's going to be like that. So set boot args and then all of our boot args. So we're going to go ahead and run it like that. So now we go print env, and we should see that it reflects that configuration change that we've made, and then we can run this boot command to boot the device up. Let's just make that go away. So here we can see that we've dropped into a different kind of root shell here, right? We are not given our login prompt, but again, this root shell is different. So it is not the jailed shell, but some of the file systems are not mounted yet. And so what we want to do to get a hint at how to mount the important file systems is we want to go actually look inside etsy initd, where it has these scripts. These scripts are, some of them are run on boot in order to fully get the device all set up and ready. And so we can look inside these. Do I have less? Is that going to actually let me use it? Kind of. Okay. Okay, here we go. So this file, S11 init here, we can see some things. It's running the mount-a command. Okay, that's interesting. It's setting up some of these kind of temp file systems here. We have some other stuff for partitions. So that's all good. And then there's actually one other one. We're not going to do a full deep dive into like how this is set up. I just have some commands that are going to ultimately, okay, it's like this S30, this thing right here. So this file is where I found a lot of the information for all of these different partitions. But there is one in particular that I am most interested in, and it's called the program partition. So right there, okay, so here we see it's like grabbing some information about this partition. Oh, this is good to know. So we can run this command. It's not, yeah, again, it's not all set up yet. So, but I have a set of commands here, which I'll just show in our text file. So these are the commands we're going to run. Again, we're going to set up those temporary file systems, and then we're going to attach, you know, to, we're going to get the UBIFS kind of subsystem set up. We're going to make this directory /program, and then we're going to mount the proper UBI partition to /program. And so again, this was kind of a tedious process of going through those files and figuring out all of these commands right here based on these two scripts. So we're going to run all those commands, and at the end of that, we can run the mount command, and we see a bunch of stuff. But most importantly, we see that the program partition is mounted onto /program. So we can go into here, into /program, and we find a number of really interesting things. So, I mean, you know, for later, we see this www directory, which is super helpful because this has got all of the kind of, you know, HTML, CSS, JavaScript, but also the backend CGI binaries that are related to the web server that is running on this camera. But for now, I want to look at bin, right? Because we are in this jailed shell environment where it's locked down, and it only lets us issue certain commands. So if you, you know, saw really fast when I ran the help command, inside of the jailed shell, there were a couple of things that were commands that were actually like labeled as .sh, which is a kind of a clear sign that what that jail shell is doing is just passing, it's just executing on the back end a shell script, right? And if we remember, I think it was this one. This is this one. That's so funny. I forget which one I modified. All right. Oh, it's system report. Okay, this one. So this command right here, system report.sh, is one of the ones that absolutely, there's probably a bunch of other ones in here, but this command was whitelisted inside of the jail shell, right? And so if we go here and look at this, I've already modified this program right here to just at the very beginning. This is my one line modification, firmware modification to bypass our jailed shell. It's just directly calling bin sh and not using, you know, some other jailed shell. So that way, when we run this from the jailed shell, we run that, you know, this system report.sh command, we should get a full shell. So let's go ahead and do that. So we've already, obviously, I've already made the firmware mod on this device. And so we are going to go ahead and power cycle to get this thing. Oftentimes when you're in single user mode, like reboot doesn't actually do what it should. So, all right, here we go. We're booting up. We're not going to stop the boot process this time. We're just going to let it go. We're just going to kind of spam enter and wait until we can give our input. Okay, there we go. I saw the root login. Some type root, password. Password is super secure, guys. All right, so we're gonna run help. So now we're back into the jailed shell, but we remember we modified this system report.sh. So now we can run this little system report.sh command, and notice our shell prompt changes. And whereas before we weren't allowed to run the mount command, now we can, and we can. I think there's like a bunch of commands that don't work. But ID does work. Okay, so now you can see we are fully root. I think this actually still reports the like jailed shell. Okay, yeah, so UVSH, Uniview shell is what I'm guessing that stands for. Again, Uniview is a camera manufacturer, but now we have a full root shell, which is a great thing for us as researchers. Now, depending on threat model, right? Let's kind of review what the impact of this is and what it lets me do as a IoT security professional, right? So first and foremost, it depends on your threat model, like we talked about in the last video. If we obtain a root shell because we were able to modify the firmware and we were able to run our modified firmware, some people's threat models, that is like a super high or critical vulnerability. And other people's threat models don't care about that, right? They're just not as concerned about this like physical access to a device, being able to modify it, being able to have it run on like unauthorized code, right? In the form of my shell script there. That totally depends on your threat model, right? But there is value, even if that's out of scope, that you if a person I'm doing this IoT assessment for doesn't care about that, this is still really helpful to get this root shell, because now I have a full unlimited shell on the device, so that now I can. What we're going to do in the next video is we're going to dump firmware using the shell. We don't have to desolder a chip now because we have a full, root shell over here. We can just go and we can just look at all the mounts, and like we saw from that script before, is it this? Is it proc? Aha, it is proc. Okay, so here we can see all of the flash partitions that are on this device, and we can use the dd command, which it does have on here. It gives us a bunch of useful commands that'll allow us to dump the firmware without ever, desoldering the chip off the device, which is nice in certain circumstances. And if we're developing an exploit, if we have reverse engineered the binaries and we think there's a network service that's vulnerable, it's so helpful to be able to potentially get your debugger to run on the target device. And so this is a stepping stone, and depending on the device threat model, this may be a vulnerability in and of itself, that it is missing an integrity check on that program file system, and we're able to modify it. So thank you for watching this video. Be sure to check out the upcoming video after this, where we are going to perform, like we talked about here, we're going to perform the firmware extraction process, and then we're going to start to analyze that firmware for hard-coded secrets, vulnerable binaries, all sorts of stuff will lead from that. Thank you for watching this video, and have a good day.